This is video 4 of the 5th topic on what makes a car go. In this video we're going to be considering forces and Newton's laws of motion.
In this video we're going to be looking at forces and Newton's laws of motion. So before we've said that a force is a push or a pull. In this video we're going to be looking at forces in a lot more detail. You're going to be introduced to Newton's laws which describe forces, and you'll see how it's vital that we have a force in order to start a car moving. Okay, so let's get straight into it. Newton's first law of motion can be written: an object continues in a state of rest or in a state of motion at a constant velocity unless compelled to change that state by a net force. So another way of stating this is that an object at rest remains at rest, and an object in motion remains in exactly that state of motion unless acted upon by a net force. So let's discuss what a net force is. A net force is actually the sum of all the forces acting on the body. So forces are vectors. When we sum vectors, we have to sum them vectorially, which means summing them up head to tail. So let's have a look at an example now of how we could calculate the net force acting on an object.
What we have here is a picture depicting a force board. So on this force board we have a central mass. There's a brass plate here with a mass of about 100 grams, and each of these little masses is 50 grams. So we've got 150 grams attached to 100 grams. So that has, these two combined have a weight force going downwards like that. Now each of these strings around the edge has 250 grams of mass attached to it. So we can represent these weight forces by lines with the same length as that first one, and we can draw all these lines parallel to our strings on top of the picture. So now, just so that we remember in which direction those forces were acting, let's draw our arrowheads. So we've now drawn all the forces which are acting in this picture as vectors. What we're going to do now is move these vectors onto the black background so that we can clearly see them, and now we will trace them out and add them together head to toe. So let's call this one number 1. So we'll trace it. There it is. And now we're going to move number 2, which is this one, so that it is head to tail with number 1. So now we can trace number 2. That's number 2. And then we'll call this one number 3. We've moved there, so now we just need to trace it. And that's number 3. Now we add the 4th one. That's number 4. And finally we move it so that we can trace on the 5th force. Now if we'd done this really accurately, these vectors would have actually formed a perfect pentagon where they were all joined up, and so this would show us that there was no resultant force. Now as this central mass is stationary, there should be no net force acting on it, because it's at rest, it's remaining at rest, which tells you that there is no net force. So these should all add together head to tail perfectly. This body is what we call in equilibrium. A body's in equilibrium when there's no net force acting on it.
So we've seen that an object at rest remains at rest, and an object in motion will remain in motion unless acted upon by an outside force. So what happens with this book if I push it? If I push it, I'm applying a force on it, So that'll start it moving. But why does it come to a stop? If you said because there's frictional forces acting on it to slow it down, then you're absolutely correct. So if there was no friction here, then this book would keep going forever. In space, if you push an object, it keeps travelling as there's no friction or air resistance in space. So Newton's first law actually leads us to the concept of inertia. A body at rest wants to remain at rest. So the inertia of a body is related to its mass. And inertia just means that a body wants to stay where it is. It's hard to start a body moving. To start a body moving, you need to apply a force, and the more massive a body is, the larger that force needs to be. So we'll be seeing why that is with Newton's second law. But let's have a look now at a couple of demonstrations showing this concept of inertia. In both these demonstrations, the bodies want to remain at rest. So what I have here is a table with a tablecloth. Here's a glass bottle of water. We'll fill up a cup of water. And now what I'm going to try and do is remove the tablecloth from below the glass and the bottle. If I do this fast enough, then the inertia of the glass and the bottle should keep them stationary where they are. Ta-da!
3.
So this is another demonstration of inertia. Here's an egg. Here's a glass at the moment. There's a plate between the egg and the glass. Now if I can remove this plate really quickly, then inertia will mean that the egg just stays where it is. So once the plate's gone, it will then experience the gravitational force, and in theory it should drop straight down and land in this glass. So let's have a try at that, see if I can hit it fast enough and accurately enough to get the egg into the cup. Ta-da! So the egg landed in the cup. As soon as the plate disappeared, the egg was left where it was and it dropped down directly into the cup. Now let's have a look at Newton's second law of motion. This is a very, very, very important law in physics. It's used an awful lot. So Newton's second law can be written: the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to the mass. So we can write it in an equation form. The acceleration of an object is equal to the sum of the forces acting on it, which is the net force, divided by the mass. Now often you'll see Newton's second law written as the net force acting on an object, so the sum of all the forces, is equal to the mass times the acceleration of the object. So we had a look at an example with the masses hanging on the board, and we saw that all the forces acting on the central mass added up to give 0, so there was no net force. So Newton's second law tells us that if there's no net force acting on it, then the acceleration of that mass is 0, which is indeed what we saw. Let's have a look at a couple of demonstrations now where we'll be seeing Newton's second law in action. So what I have here is a heavy mass and a hammer. Now if I was to whack my hand with the hammer, that would hurt a lot because the force from the hammer would all be imparted into my hand and that would hurt. If, however, I put the heavy mass on my hand, then it doesn't hurt if I whack the heavy mass with the hammer, as, let's have a demonstration of that. See, didn't hurt, came back for seconds. So that doesn't hurt in this case because this force is being distributed over a much larger mass. And so the acceleration of this block acting on my hand is actually a lot smaller. And so the total force applied on my hand is smaller. So what I have here is a trolley. It's got a mechanism so that when I push down here, this thing shoots out here, which is going to be up against the wall, and so that will cause a force pushing the trolley along the ground. So we're going to try this with different amounts of mass placed on the trolley, and you can observe the acceleration in the different cases. Each of these masses is 1 kilogram.
And here is the slow action replay so that you can see that the one with the most mass accelerates much less than the one with less mass. Let's do a couple of examples now of using Newton's second law to solve problems. So the problem is, a car is stalled. The car has a mass of 1,100 kilograms. Two people push the car, one with a force of 3,050 newtons and the other with a force of 4,200 newtons, which is directed in the same direction as the first force. A frictional force of 6,100 newtons opposes the motion of the car. Part A, calculate the net force on the car. Part B, calculate the acceleration of the car. Okay, so it's always a good idea to start questions by drawing a diagram. So let's draw a diagram. Here's our car. It's got two people pushing it. One with a force of 3,050 newtons, the other with a force of 4,200 newtons, and then we've got a frictional force opposing the motion. So in the next topic we'll be looking in more detail about this frictional force, but that's 6,100 newtons. Now to calculate the net force, what we need to do is sum all these forces together. So we can draw them head to tail. So we've got 3,050, and then a slightly longer one of 4,200, and then one going back in the opposite direction of 6,100 newtons. So this here, from here to here, is our resultant force. So to work out the size of this resultant force, we've got 3,050 plus 4,200 minus 6,100, as this one's in the opposite direction, and so it subtracts. And so solving that, we get 1,150 newtons. And since it's a force, we should give a direction. So the direction of the force is in the same direction as the people pushing. So in the same direction as the people push the car. Now part B asks us to calculate the acceleration of the car. So to do this, we'll need to use Newton's second law. The acceleration is given by the net force over the mass. We've calculated the net force here, it's 1,150 newtons, and the mass of the car, we're told, is 1,100 kilograms. And so the acceleration in this case is given by 1.05 meters per second per second. And now as it's an acceleration, which is a vector, we should give a direction. So the direction of the acceleration is the same as the direction of the net force. So in the same direction as the people pushing the car. Okay, so that was a relatively straightforward example where we only had to worry about the horizontal components of the forces. Let's have a look at a more complicated example now. In this example, we'll also be introducing the normal reaction force. So a rope is used to pull along a block as shown in the diagram. So here's the diagram. We're applying a force of 30 newtons at an angle of 30 degrees to the horizontal, and the block has a mass of 2 kilograms. Part A, will the block be lifted off the surface in this case? Part B, what is the net force acting on the block? And Part C, what is the acceleration of the block? So this is a relatively difficult problem. To do Part A, we're going to need to consider all the forces that are acting in the vertical direction. So when we have a block like this, we've got the weight force acting downwards, we've got the normal reaction force from the table acting upwards, and then in this case we've got an additional force here, we'll call it force Y, which is the vertical component of this applied force here. So we can use SOHCAHTOA to work out the size of this force, force Y. So we have got force Y is opposite the 30 degrees, and we've got the hypotenuse. So we'll be using sine of 30 is equal to the opposite, which is force Y, over the hypotenuse, which is 30, which tells us that force Y is equal to 30 times sine 30, which when we solve that on the calculator, we end up with 15 newtons. So we've got an upwards force of 15 newtons and a downwards force equal to mg. The mass is 2 kilograms and g is 9.8, so this is equal to 19.6 newtons. So our weight force is larger than our upwards force. So that tells us that it's going to remain on the table. This normal reaction force will be the size of the difference of these two forces, so that vertically it's in equilibrium because it's not being lifted up off the surface and it's also not falling through the surface, so it must be stationary in the vertical direction. So this tells us it is not lifted off the surface as the upwards force is not greater than the weight force. So if we wanted to, we could calculate this normal force. We know that 19.6 downwards has to equal the normal force upwards plus the 15 newtons upwards, and so our normal force upwards is equal to 19.6 minus 15, which is equal to 4.6 newtons upwards. The question didn't ask us to do this. This is just for an example. B, what is the net force acting on the block? So we've said vertically there is no net force as these forces all balance each other out. The downwards weight force is balanced by the normal reaction force plus the upwards component of the applied force. This 30 newtons is the applied force. So the net force acting on the block is only the horizontal component of this applied force. So we've got 30 newtons and 30 degrees, and we'll call this Fx, the horizontal component. And so we can use SOHCAHTOA. We've got the adjacent in this case and the hypotenuse. So we need to use cos. So cos of 30 is equal to the adjacent, which is Fx, over the hypotenuse, which is 30. So this tells us that f of x is equal to 30 times cos 30, which is equal to 26.0 newtons. And this is also the net force. So in this case, this is to the right. We need to give a direction as a force is a vector. And then finally, part C, what is the acceleration of the block? Well, from Newton's second law, the acceleration is equal to the net force over the mass. So we've got our net force, it's 26.0 to the right, divided by the mass, which is 2. And so this is equal to 13 meters per second to the right.
So this brings us to Newton's third law. Newton's third law says that whenever one body exerts a force on a second body, the second body exerts an oppositely directed force of equal magnitude on the first body. So sometimes this law is stated as, for every action, there's an opposite and equal reaction. So one example of this is when I sit on the chair. I have a weight force of mg acting downwards onto the chair. As a result of this weight force, the chair provides a normal reaction force of equal magnitude pushing me upwards. If it didn't do this, then Newton's second law says that there would be a net force acting, and so I would accelerate downwards. And clearly, I'm not accelerating, I'm stationary. So because I have a weight force, there is a normal reaction force acting upwards as well. Another example of Newton's third law is with a balloon. If I release this inflated balloon, air rushes out this way. So there's a force from the air molecules being accelerated out this way, and the balloon experiences a resultant force in the opposite direction, causing it to fly away. Let's have a look at another demonstration now. This is Dr. Julian Berengut, who's a theoretical physicist in the School of Physics. He's going to help me demonstrate Newton's third law. So what I'm going to do is I'm going to pull on this rod here. Can you predict what's going to happen when I pull on the rod? Okay, here it goes. So did you predict that we'd both move? Newton's third law tells us that when I apply a force on this rod, then the rod applies an equal and opposite force on Julian, moving us both together. Now look at what happens when I push off in the opposite direction on the rod. We both start to move apart. So in this video, you've met Newton's 3 laws of motion. You've seen an object at rest will remain at rest, or an object moving in motion will remain in constant motion unless acted upon by a net force. You've seen that the acceleration of an object is equal to the net force acting on it divided by the mass of the object. And you've seen that for every action, there's an opposite and equal reaction. You've also seen how to calculate a net force. To calculate a net force, you need to sum all the forces acting on a body, and because they're vectors, you need to sum them by adding them head to tail. So let's discuss how this is related to what makes a car go. Newton's first law tells us that if a car's at rest, it's going to remain at rest unless it's acted upon by a force. So the engine is going to provide a force to start the car moving. Newton's second law tells us how the car accelerates. So the car accelerates with an acceleration equal to the sum of all the forces acting on it divided by the mass of the car. And finally, Newton's third law tells us that we need a reaction force for the car to start moving. So generally, the friction on the road provides a reaction force so that there's a force backwards and there's a force forwards on the car. Now, if a car tries to start on an icy surface with very little friction, the wheels can start spinning as there is no reaction force, and so the car cannot experience a forwards force. Now, I recommend that you have a look at Joe Wolf's Phys Clips. He has an excellent section that cover Newton's laws of motion.
Special thanks to Sebastian Frick for filming and to Dr. Julian Berengut for appearing in this film.